you can check on. What if there is clustering? In the previous lecture, I talked a little bit about clustering, where instead of rolling the dice per units in a unit cell for each indium and gallium atom for the alloy, you could just throw the dice for a unit cell by unit cell. That would give you little chunks of indium arsenide, and the chunk would contain 8 atoms, because a unit cell is made up of 8 atoms in the NEMO simulator for zinc blender. And in the next unit cell, you roll the dice again. Right? So you kind of make more chunky quantum dots like that. So if you do that, so in the top line you have the same blue, dark blue distribution function. They are translated into the lower row now as dark blue. And you see that the valence band, when clustered, moves up in energy a little bit in light blue. The conduction band roughly stays put but gets broader. And overall then the band gap gets a little narrower, which again is kind of reminiscent of cold temperature or lower temperature clustered growth in gallium arsenide, where the gap gets a little bit smaller. All right, so now also the sigma, the gap of the sigma goes from 2 to 4.5 milli-electron volt. So also the distribution function gets broader. Okay, so clustering makes the line width a little bit broader. Okay, so it makes a difference, and it increases the noise, and it shifts the valence band, and it decreases the gap. So why does the noise increase? So here I had shown on the bottom left now, in dark blue is the correlation function for the case where there is no clustering, and in light blue there's the correlation function in dark blue. So they both have similar band correlations. Again, if a conduction band goes up, valence band goes down, and vice versa, right? So that doesn't quite explain why the noise really increases. We can plot for this histogram, we can plot the indium concentration. So again, we have not exactly counted the number of indium atoms in the system and kept it exactly to be the same. There is a statistical noise on that, but that seems small. And if you correlated this indium concentration against, say, the conduction band edge, so for each sample we can measure how many atoms of indium do we actually have in the system, and are we hitting exactly 60%? And if we measure where the conduction band edge is, we can put a dot on this scale, and roughly you see a roundish distribution. That means that correlation or the noise is not really due to the indium concentration fluctuation, right? There's no correlation against that. So the only thing that we feel is really left over is that there is the larger crystal distortions, which lead to larger wave function distortions, which lead to larger delta E's. So it's really the local arrangement of the wave functions feeling the order and the clustering that gives you more fluctuations. So here's the irregularity in these whole ground states again as a reminder. So different samples will vary from one to another. And the bottom line in this question that we asked, if you could do this Gedanken experiment of controlling size, shape, height, number of atoms exactly, experimentally, your gap, your optical interband transition would have a noise of 5 milli-electron volts, thereabout. Now experimentally, Rosa Leon at JPL has measured 35 milli-electron volts in a system like that. And she has, of course, not had extremely well control of size, shape, positioning, right? That tells me that at least out of those 35 milli-electron volts, that alloy disorder could have played a significant part, even if she could have placed these quantum dots exactly and made the size bigger. The lowest you can get to is roughly 5 milli-electron volts. That means if you really wanted to have a really quiet laser that is really tuned to exactly that particular frequency, and all these dots had to be identical, an alloyed system is probably not the right thing. Going in further, I would say, if you have a nanostructure and you need to control its size and shape and configuration, alloys are hard things to deal with because you don't have good control. So, are there any questions on that? Yeah?
Do you study what happens to the polarization? Because destroy in some way the symmetry of the states, I expect different effects on.
We haven't done that. That's a good point. We haven't studied the polarization. That's a very good point. We could have done that, but we haven't done that.